Okay then, so I'd like to start this lecture with a discussion of limit points. So this is an idea which helps us to understand much better what open and closed sets really are, and helps us to draw even more parallels between the familiar real numbers and general topological spaces. So thinking about real numbers, we could consider a sequence like this: 0.1, 0.01, 0.001, 0.0001, etc. And it seems pretty clear that this sequence is approaching zero, although it won't actually ever get there. It'll get arbitrarily close to zero. So we say that zero is a limit point of this sequence. Now, what we're going to do is define limit points for topological spaces. And we're going to do it without referring to distances at all. We're just going to do it in terms of the open sets. So this turns out to be a very profitable thing to do. So let's write down our definition. So suppose we've got some subset of our space, of our topological space, and suppose we've got some points in the space, little x. Now we'll say little x is said to be a limit point of A if, so I'm using if with two F's here, that's just mathematicians' shorthand for if and only if. So it's a limit point if and only if every open set U in our topology contains a point of A other than X. Okay, so let's try and understand this this definition a little bit better. So one good way to start is just by writing it in a simpler, more compact form. So we can write it like this and say that a point is a limit point of A if and only if for every open set we have that the intersection of that open set with the set we get by taking A and removing the point x, little x, if it's in A, is non-empty. So this says the same thing as what's written in black above. It's a more compact way of defining what a limit point is. Okay, so let's look at the scenario diagrammatically as well, just to hammer it home. Whoops. Okay then, so suppose this is our space X. This is our topological space. And suppose we've got some subset of the space A. And suppose we've got some point in this space, or we'll call it little x. Now, little x is going to be a limit point of this set A. It could be inside or outside A, but the condition we need is that each open set U, which contains x, so there's one open set. Let's say that this is another one. Maybe this is another open set called U dash. So each of these open sets which contain x must contain a point of A which is not equal to x. That's our condition for x being a limit point of the set A. So let's have a look at an actual concrete example. So let's suppose that we have the set x equals A, B, C, and our topology, we'll take a simple case, consists of the empty set, the set of x itself, the singleton set containing A, and the set containing B and C. So let's just check this is a topology. Okay, it's got the empty set, it's got the whole set. Intersection of those two is the empty set. Union of those two is the whole set. So yes, it's a topology. Now, suppose we pick our set capital A to equal C. So does C have any limit points? If so, what are they? Perhaps you'd like to pause this video now and try and figure out that, try and answer that question. Okay then, so it turns out that B is a limit point of A. Why is that the case? Well, because every open set which contains C, so there's only two of those, this one and this one, both contain, every open set which contains B, namely this one and this one, contain a point of A. They contain point C. So we have this condition that every open set containing our point B contains a point of capital A which is not equal to B. Therefore, little b is a limit point of the set capital A consisting of a singleton C. So here's a practical example. Okay then, so now let's have a look at some interesting kinds of studies about limit points of topologies we've already spoken about. So what about the discrete space? recall that the discrete space is where the topology is just equal to the set of all subsets of X. What are the limit points of a discrete space? Again, maybe you want to pause the video and see if you can answer this question. Well, the truth is that the discrete space has no limit points. So why is that? Well, the point is that for any point, so let's just do a little proof of this. For any member of the discrete space, little x, we have the set containing x is an open set, and it just contains x. So no matter what set A we're thinking about limit points with respect to, there's no way that this little x could be a limit point of that set, because there is an open set which contains that little x, only contains that little x. Therefore, there's just no way that this condition here could ever be met. So yes, the discrete space has no limit points. Here's another problem that you might want to think about, and it's about okay, so it's a problem for you. What are the limit points of this half open set A, B in the Euclidean topology? So this set here, we have, just to tell you what this notation means, we have A is going to be less than B, and this is equal to the set of all equal to the set of all real numbers R, such that A is less than or equal to R is less than B. Okay, so what are all the limit points of this set? I'll leave that to you as an exercise. And another question for you. Okay, let's rephrase it. Suppose that X is a set. Hang on. Excuse me. Suppose that A is a subset of X such that the number of elements in A is greater than or equal to 2. Okay, so in general, I use this kind of notation here. This means the number of elements in A. Okay, so suppose we've got this going on. We've got this subset with at least 2 elements. Whoops. And suppose that X tau is the indiscrete space recall that the indiscrete space is the space where the only open sets are the empty set and X itself. Now our question is just, what are the limit points of A? So those are good questions to think about. If you can answer those, then you've probably absorbed this definition of limit points quite well. Okay then, so time for one of the major results about limit points. This is a really important result in topology. And so we'll call it proposition A. And it goes as follows. Let X tau be a topological space, any topological space. Now, our result states that a subset of X is closed in this topology if and only if this subset A contains all its own limit points. So this is a really useful result because it gives us a new way to characterize what closed sets are. We can characterize them in terms of limit points. So a set is closed when it contains all its own limit points. So if you recall the example at the beginning, when I was saying that a limit point of the sequence, so the sequence 0.1, 0.01, 0.001, this sequence has a limit point of 0. Well, what that implies then is it implies that the set of numbers which are greater than 0 and less than or equal to 1 does not contain all its limit points, because it does not contain, it doesn't contain 0, okay? Doesn't contain 0, so it doesn't contain all its own limit points, and so what that means then is that this set here is not closed. That's an implication of proposition A, amongst many others. Then, so let's do a proof to proposition A. So we'll start by showing the argument this way. That is, we're going to show that if a subset of the space is closed, then it contains all its own limit points. So rather predictably, we'll start by assuming that we have a closed set, a closed subset of the space. Now, I know it's trivial, but let's just note that the complement of A is open. That would be important. Now, what we're going to do is a proof by contradiction. So we want to show that A holds all its own limit points. So we're going to assume that that's not the case, and we're going to assume that there is a limit point of A which is outside of A, and then we're going to derive a contradiction. So I should put suppose in red. since this is the start of our reductio ad absurdum argument, suppose that little x belonging to the complement of A is a limit point of A. Now we get our contradiction, because if we define u to be equal to x take away A, the complement of A in other words, well, we know that u is an open set. U is an open set containing x. And what do we know about limit points and open sets which contain them? Well, we know that since U is an open set containing x, if x truly is a limit point, then this open set should intersect with A. It should contain points of A other than x. So if x is truly a limit point, then we would have that U intersection A is got to be non-empty, because it's an open set containing little x, and it's supposed to be a limit point of A, so it should intersect with A. This open set should intersect with A. But what's the problem here? The problem is that this statement here, U intersection A is non-empty, is precisely the same as saying that x take away the complement of A intersected with A is non-empty, which is ridiculous. So that's a contradiction. So just to recap, once we assumed that there was a limit point of A which is outside of A, we got a contradiction. So it must be the case that this close to A contains all its own limit points. So that proves the argument in this direction. Okay then, so we're going to assume that A contains all its own limit points. Another way of saying that is that every point outside of A contains all its own limit points. So another way of saying that is that every point outside of A is not a limit point. So let's write that explicitly. So now for every point Z which is not in A, in other words, which is in the complement of A, we have that Z is not a limit point of A. So what does that mean? Well, it would be a limit point of A if every open set which contains it intersects with the point of A. But we're assuming that it's not a limit point of A, so there must exist an open set around this point Z, which we shall call UZ. It's an open set, and obviously Z has to be inside it, and also it does not intersect with A. Okay, so we have that for every single point outside of A. So what does that mean? Well, we have one of these open sets for every point Z outside of A. So if we just take the union over all of those points, so we take the union over all Z in the complement of A of these special open sets uz, well, we know that the intersection of that with A is equal to the empty set. Okay? And a little bit of thought should convince you that this statement is equivalent to the statement that the complement of A, is equal to the union of all of these open sets which crop up in the complement of A. Oops. Okay. Now, we know that each of these sets uz is open, and we know that the union of open sets is open, so this is open. So we know that A is the complement. So we know that A has a open complement. So if X take away A is open, then A must be closed. So this implies that A is closed, which completes our proof. Okay, so proposition A has some very powerful applications. So just to list a few, suppose for example that we wanted to prove that this set here, the set of all integers greater than or equal to A and less than B, is not closed. So how can we prove that quickly? Well, we can prove it very quickly using proposition A, because basically proposition A says that a set is closed if and only if it contains all its own limit points. Well, B here is a limit point of this set. So B is a limit point of this, but B is not contained within this set. And therefore we immediately have that this set is not closed. Also, for example, if one's considering the set of integers greater than or equal to A, all the way up as big as you like, we can show that that set is closed simply by showing that it contains all its own limit points. And that's fairly easy to see, because if we look at the complement of this set, we'd see that every point in this complement here is going to have an open interval about it, which is contained within this set here of integers which are less than A. Sorry, real numbers which are less than A. These are all sets of real numbers. Okay then, so these are a couple of practical applications of proposition A, but some things it's really useful for are proving more general results. So I want to introduce an important concept called the idea of the closure of a set. But before I do that, I want to establish the main proposition which really gives validity to that property. So it's another very important result. We'll call it proposition B. So what proposition B says, it says that suppose we've got a topological space, x tau, and let A be any subset of that space, and let A dash be the set of all limit points of A. Now what our result says, what proposition B says, is that A union A dash is a closed set. So it's quite a remarkable claim. It says that if you take any subset within a topological space, and you take that subset in union with all of its limit points, then the result is always going to be a closed set. So the proof of this is also quite constructive. So let's take a look at the proof. To do the proof, let's start just by taking an arbitrary point P, which is outside of the union of A and A dash. So it's in the complement of A union A dash. Remember, A is just an arbitrary subset, and A dash is the set of limit points of A. Okay. Right then. So our first claim is that P is not going to be a limit point of A. Okay? Why is P not going to be a limit point of A? Well, the basic reason is that all the limit points of A are in the set A dash, and we know that P is not in the set A dash. So let's write this down. So since A dash is the set, okay, so I'm writing the proof here, I might as well write proof at the top. Since A dash is the set of all limit points of A, and P is not in A dash, P is not a limit point of A. So what does that mean? Well, what it means is, from the definition of a limit point, it means that there must exist an open set U which contains P and which is such that U intersection with A minus the point P is empty. Okay, a simpler way to say this is that either U intersection A is empty, or U intersection A just consists of a point P. Okay, so why is this true? Why must there exist this open set like this? Well, the reason is that if there was no open set which was like this, then it must have been the case that every single open set which contains P would have to intersect with some point of A other than P. And if that was true, then P would be a limit point of a set A. But we just showed that P is not a limit point of a set A, so there must exist one of these special open sets which kind of keeps itself to itself and doesn't intersect with A, or at least if it does, it only touches the point P. So we know that either this condition here must hold or this condition here must hold. However, this condition here, that U intersection A is equal to the set containing P, just isn't possible, because we know that P does not belong to A, because that's how P was defined up here. So since P is not in A, this just isn't possible. And so we must in fact have that this open set U just doesn't intersect with A at all. Okay, we're getting there now. Okay, so we've shown that this open set U around P does not intersect with A. So in a way, we're kind of halfway there towards the end of our proof, because the next thing we want to show, which will kind of get us to the end, is to show that this open set U also does not intersect with the set A dash. So this is our next claim. So we want to note or claim or prove that U intersection A dash is empty. Okay, so why is that the case? Well, let's think about what happens otherwise. If that was not the case, otherwise, of course, there'd have to exist a point, which is in the intersection. Actually, I'll write it down there so I don't get the pen messed up. Okay, so if it wasn't the case, obviously there'd have to exist a point, X, which is in U and A dash simultaneously. And now U is an open set containing, excuse me, I'll have to rewrite that. It's an open set containing X, which does not intersect A. Okay, well, we know it doesn't intersect A from up here. Okay, so we know now that X is this point and it has this open set around it which doesn't intersect A. But now we're getting into difficult territory, because now we've contradicted our definition of A dash, because that now what that implies is that X is not a limit point of A. Okay, why is it not a limit point of A? Well, because it has an open set which it's contained within, and that open set doesn't intersect with A at all. So it has one of these open sets that keeps itself to itself. So X is not a limit point of A, but we just said that X was in the set A dash, and we defined A dash as a set of all limit points of A. So this is a contradiction, isn't it? It's a contradiction. The contradiction is that we can't have that X is not a limit point of A, while x belongs to a dash, which is the set of all limit points. Okay, so if this is not true, if u intersection a dash is not true, we get a contradiction. So u intersection a dash must be, if the intersection of u and a dash is not empty, then we get one of these points x, which is not a limit point of a, which gives us a contradiction. So in fact, it must be the case that u intersection a dash must be empty. There can't be any points in this open set u and in a dash at the same time. Phew, okay, so we've got this next point established, and now we're on the home run. So the proof's fairly straightforward from now on. Perhaps you can pause the video and finish it off. So now we have these 2 points here and here. We just get that u intersection a union a dash is empty. Okay, so what we've essentially just shown is that I'll write it in red now just to change the colours. We've shown that for every single point outside of a union a dash, there exists an open set u which doesn't intersect with a union a dash. So what this basically means is that no limit point of a union a dash is in the complement of a union a dash. Okay. Another way of saying that, maybe I'll just make a bit of space. Oh, I don't know. I'll just write it up here. Let's make a little bubble up here to write in. So another way of saying that is that a union a dash contains all its own limit points. Hooray! And what does that mean? Well, according to proposition A, when a set contains all its own limit points, it's closed. So this then directly implies that A union A dash is closed, which finishes our proof. We can use proposition B to give us a really powerful and simple new notation, the idea of the closure of a set. So let's define this properly. So for a topological space, x tau and a subset of that space A, we call the union of A with all its limit points the closure of A, and we write it as A bar. So to find A bar, you find all the limit points of the set A, and then you take the set A in union with all of those limit points. That gives you the closure. So it's really neat because it's really easy to write it. You just put a bar over the top of something to denote the closure. But it's an extremely powerful concept. And there are some other ways to think of this concept as well. So I'm not going to prove this. I'll leave this as an exercise for you to prove. But it's an interesting thing to remark that the closure here, so this is another result. I'll say it's a claim because I'm not going to prove it. The claim is that the closure of A is the intersection of all closed sets containing A. So that's a very neat way of thinking about what this is. Another way to think of it is as the minimum sized closed set, which contains A. Okay then, so let's just cement some of these ideas now. So we'll take a look at a sort of toy example. Let's consider the topological space with a set X equal to A, B, C, and the topology consists of the empty set X, A, and BC. Now the question is, what is the closure of the set which just contains B? That's the question. So perhaps you'd like to pause the video and see if you can figure this one out. It's a good way to test if you've absorbed these ideas. Okay, so there's a couple of ways we can attack this. Using the claim I just made, the closure of the set just containing B ought to be the smallest closed set which contains B. Now actually this topology has a rather interesting property. You see, these are all the open sets. So we ask, what are the closed sets? And the closed set, so let's just write them up here. So the complement of the empty set is X. The complement of X is the empty set. The complement of A is BC. And the complement of BC is A. So interestingly, the set of open sets is absolutely equal to the set of closed sets. So it makes things a bit easier. So anyway, we could use the previous claim, after you've proved it, And then you get that the closure of a set is just equal to the smallest closed set which contains it. So what's the smallest closed set which contains B? Well, it's this, isn't it? So this ought to be our answer. We ought to have, according to this little argument, that the closure of the singleton set which just contains B is equal to the set BC in this topological space. Okay then, so let's try and prove that this result here is true using the idea of limit points. So remember, the closure of a set is equal to that set in union with all of its limit points. And P is a limit point of a set when every open set which P is a member of intersects with a member of that set, which doesn't equal P. So by that logic, we see that the well, if we have a look at point C here, then indeed this does have the property that every open set which contains C, like there's only two of them, this one and this one here, they both contain B, and B is a point other than C. So indeed C is a limit point of B, and in fact it's the only limit point of that. So in other words, what we have is that the limit points of the set B is just equal to just C, and so when we take these two in union, we get BC, which is indeed the closure. So there we have it. Okay then, so I don't necessarily agree with all of the terminology which topologists have invented. I mean, sometimes the whole idea of calling things open and closed seems a bit questionable to me, but I think this next definition does have a really sort of meaningful name. Like, the name really says it all. So I'm going to tell you about a concept of a set being called dense, or everywhere dense. So let's give this definition. So as usual, suppose we've got a topological space. And let A be a subset of that space. Now, we say that A is dense, or sometimes we say it's everywhere dense. These are two terms that mean the same thing. We say in X when the closure of A equals X itself. So we say that a set is dense in X when, if we take the closure of that set, we get X. So let's look at a fairly trivial example, just to illustrate the point. So suppose X tau is the discrete space. Well, in the discrete space, every subset of X is open. So every subset of X is closed. So every subset of X is equal to its own closure. And so the only set that's closure is equal to X is X itself. So here, X is the only set that is dense in X. But you can have other much more interesting examples. So if I can just fit it on the bottom of the page, a very interesting case is the rational numbers. So if we take the Euclidean topology and we take the closure of the rational numbers, then we get the set of real numbers. I'm not going to prove that. Maybe you'd like to go through the argument about that yourself. So let's do one more proposition, and this time we're going to use this concept of density. So proposition C. This is going to illustrate what a powerful claim it is to say that a set is dense in a topological space. So let A be a subset of a topological space X tau. Now we have that A is dense in the space X if and only if we have that every non-trivial open set intersects with A. So for every open set U, such that U is not empty, we have that the intersection of A with U is also not empty. That's our proposition, that's our claim. So let's try and prove it. Okay then, so now let's give a proof to proposition C. So we're going to start our proof by showing the argument in the left direction. So we're going to begin by supposing that for every non-empty open set, we have that the intersection of A with that open set is non-empty. And we're going to try and show that this implies that A is dense in X. So here goes. Let's consider two cases. Firstly, what about the case where our set A is just equal to X? Well, in this case, the argument's easy. Then it's kind of trivial that A is dense in X. Why? Well, I mean, obviously, the closure of A is going to be equal to X if A itself is equal to X. It's equal to the whole space, right? Let's look at the other possibility, which is a bit more interesting. So if A does not equal X, what then? So in this case, we can choose an element x which is not in A. So it's in x minus A, as I like to say. Now we can also choose an open set which contains this element x. So let's consider such a thing. It's an open set U. And x is a member of it. Well, the thing is about U, it has to have a non-empty intersection with A. Because our assumption is that every non-empty open set has a non-empty intersection with A. That's our assumption up here. And so what we actually have is that x is a limit point of A. Why is that? Well, because we have this open set which contains x and contains points of A. So x is a limit point of A. And so basically, this argument holds for arbitrary x outside of A. And so what we have now, we have that basically we've shown that for every single element which is outside of A, we have that element is a limit point of A. So we take the closure of A, that's equal to A in union with all of its limit points, that must be equal to the entire space X. So the closure of A equals X. And that's just another way of saying that A is dense in X. So that completes the argument in this direction. Okay, so let's try and prove the converse result. So suppose now that A is dense in X. Right, so what we're going to do now, we're going to think about an open set. So let U be a non-empty open set. And we're going to suppose something that's false. And we're going to try and find a contradiction. So we're going to suppose that the intersection of U with A is empty. Now that's not going to be true, but we're going to derive a contradiction from it, okay? We're going for a reductio ad absurdum argument. So suppose that the intersection of this open set with A is empty. Now, what's that mean? Well, there's got to be a point in this empty set. Sorry, there's got to be a point in this open set. Jeez. Yeah, there's a point in this open set, U, which we're going to call little x. And little x is outside of A because U and A don't intersect. Now, this implies that x is not a limit point of A. Okay? This is important, right? So basically, why is it not a limit point of A? Well, the reason is that there's an open set which contains it, which doesn't intersect with A. So there's no way it can be a limit point of A. The problem here, though, the reason we've got a contradiction is because we have that A is dense in X. So what this implies is that the closure of A must be equal to X. So that implies that each point, which is not in A, must be a limit point of A. But here we have that there's a point X not in A, which is not a limit point in A. So these two remarks here, they contradict each other. We have a contradiction here. And the presence of this contradiction means that this here must be false. And so in fact, in order to escape contradiction, we've got to change this thing I've just underlined in blue. And in fact, what we must have is that for every open set, which is non-empty, we must have that the intersection of that open set with A has to be non-empty. And that completes the argument in the right direction and finishes the proof.